So there's one more kind of connective tissue that I want to talk about this week, and that is cartilage. And as I'm sure you are familiar, cartilage exists between bones, meaning it makes up the two surfaces of, say, two bones that are in contact with each other. Each of them has cartilage on the surface to protect and to cushion and to lubricate the joint space. So cartilage is made of collagen, but it's made of a different type of collagen. Something I haven't talked about so far is there's actually two types of collagen. There is type 1 collagen, which is found in bones, your skin, tendons, ligaments, and a few other places. And then there's type 2 collagen, which is found in cartilage. And it has some different properties that make it a little bit less straightforward in the same way as, saying, comparing tendons and ligaments, which are really quite similar. So first of all, this type 2 collagen in cartilage is not aligned in nice fibers. It kind of forms this weird web-like matrix, as compared to tendons and ligaments, where we had these nice kind of wavy, aligned, almost like rope or cable-like structures. It forms this three-dimensional like matrix material. There's actually a lot of different types of cartilage, but we care most in this class about what's called articular cartilage, meaning art joint. Let me write that out. Articular cartilage. Sometimes you'll also see this called hyaline cartilage, and that is spelled hyaline cartilage. I tend to use articular cartilage because it's a little bit more descriptive of a term. Arthritis, that term, right, uses the same root. It tells us we're talking about joints. So cartilage is fairly strong and it's fairly rigid. And for a long time, people thought that cartilage was the primary shock absorber between, say you're running or doing plyometrics or something, and a big impact shock goes up your leg. For a long time, people thought cartilage did that shock absorption. It turns out that it is more the bone here and here. There's a specific region of bone called subchondral bone. It's mostly trabecular bone. It's called subchondral. It means below the cartilage. Mostly trabecular bone, which you know from last week what that is. And actually, it turns out that stuff does most of the shock absorption, not so much the cartilage. And I think the intuition for that is that you have a lot more space to do it versus cartilage, which is actually quite thin. Your layer of cartilage is relatively thin. However, cartilage does have a very important role to play in reducing friction. So at the very end of last week, I tacked on a little video about understanding friction for those of you who haven't taken physics or who took it a long time ago. And I put this one equation in: the force of friction equals this thing called the coefficient of friction multiplied by the normal force. And we said in the context of a joint, that normal force is like the joint contact force, meaning how hard, say, is the femur pushing into the tibia and vice versa, right? Because if you say this person's doing a squat, they've got the weight of the barbell and their own body weight pushing down like this, and an equal and opposite reaction from the ground. And of course, you have the forces from the muscles, like this and like this and like this, all pushing together that joint space. So there's a large amount of joint contact force that can be several times your body weight. I think this was on the comprehension quiz from last week. And the correct answer was many times more than your body weight, not just about the same as body weight plus whatever weight you're carrying. So let's say we're in a situation where we have like 1,000 pounds of joint contact force. The force of friction is going to be how much resistance is there going to be to these two bones sliding relative to each other. In other words, how hard is it going to be to rotate the joint? Well, it turns out that in a healthy cartilage, healthy articular surface, that coefficient of friction is really small. It's like 0.01 to 0.001. So even if you have 1,000 pounds of joint contact force, there might be 1 pound of friction force. So that's very handy. Now the problem, or the where this can go wrong, is in arthritis. So when people get arthritis and their cartilage deteriorates, by the way, a little terminology there. Arth meaning joint. Itis, like in the last video, inflammation. Arthritis is an inflammatory condition, and it does affect the cartilage and also the subchondral bone. What happens there is that these surfaces don't slide well relative to each other anymore, and there's actually much more friction. So in addition to the pain and damage caused by arthritis, it's also physically more difficult to move the joint because the properties of the cartilage have changed. So one other thing I want to cover in this video, pertinent to this complex matrix-like structure of cartilage, is as follows. Let's say we had like a big chunk of cartilage here, and it's got this kind of complex three-dimensional collagen structure. Much of the mechanical integrity and much of the weight of this cartilage comes from water. So it's like a sponge. Cartilage can be up to like 95% water by weight. And so a consequence of that is that if you apply a load to cartilage for a long time, like minutes, hours, it will actually squish out the water, and it will become less springy and less mechanically strong. When I was preparing materials for this class, I saw a study that came out this December that showed a really cool example of that. We are looking at the articular surface of the knee. So this is like a top-down surface of the tibial plateau. And this study looked at how thick is the cartilage before and after either a 3-mile run or a 10-mile run. And you can see the thickness, more red means more thicker cartilage. And you can notice, say, looking at people who do a 10-mile run, the apparent thickness of their cartilage actually goes down after a run, but then it comes back after a day of recovery. So this isn't because the run is damaging the cartilage. It's because it's like a sponge that's getting squished out. The water is getting squished out of that cartilage. Oh, and I think I may have misspoken. This is the cartilage on the back side of the patella, not the underside of the knee. So we're looking at this cartilage right here for this bone-on-bone junction. So what's happening there is that before the run, the cartilage is like this, kind of like a sponge. And then you run, you load it a bunch, and it gets kind of like squished like this. And then after some recovery, water diffuses back into it, and then it swells back up to this nice size. So I thought this was a super cool way of looking at this sort of sponge-like property of cartilage.